Hi. So thanks, Chris. I'm Alex Singh from the University of Glasgow. So the work I'm presenting today was done with our project partners at Bosch, which looks at different input controls for in-car touchscreens. So one of the main motivations. So one of the main motivations for the study is that touchscreens are getting very popular with cars, replacing like physical buttons and dials and switch gears. So the most extreme example we see is at Tesla, replacing almost all the buttons on their center console with a touchscreen. So this gives designers opportunity to design new interaction techniques. So there's always been a lot of studies looking at touch input with touchscreens and looking at how drivers perform input performance and in terms of driver distractions. So one of our key motivations was look at a different type of input. So we looked at pressure-based input, which is becoming more common with very popular devices like the Apple iPhone. Before Apple introduced the iPhones, there was lots of research from Kai and Mobile HCI looking at different types of design of pressure input and how we can use that to interact with our touchscreen devices. But in terms of the car domain, there hasn't been that many studies that have looked at how can we use pressure input for in-car touchscreens, and we think that in the future it's likely to feature on the center console. So last year in haptics we saw a demo of the force pad. We compared the performance of touch input, physical input, and pressure-based input for in-car touchscreens in real-world driving situations. So we've done a few studies using driving simulators, and we've actually got users to sit in the passenger side seat. But we went one step further with this study, where we really got them to drive in the real roads and do our task. So now I'll explain the design of our study. So this is just a quick image of a participant performing the task while driving. So we use a list-based targeting task. So lists are very common with touchscreen applications, so selecting songs from a playlist, and it allows us to have a fair comparison of the input techniques I'll be talking in a few slides' time. So it's a non-scrolling task, so we had 10 abstract numbered items. Each item measured 16 millimeters and ran on our Surface Pro 2. So we tested 4 input techniques, first being pressure-based buttons. So we used 2 force sensors to allow bidirectional cursor movement, so the user can move up and down the list. So we placed both of these sensors on a 3D printed case, which I'll explain later in a few slides later. So users, to move the on-screen cursor, users had to apply 3 newtons of force on either of the sensors. So applying 3 newton force on the left sensor moved the cursor down, and 3 newtons of force on the right sensor moved the on-screen cursor up. So the user had to lift off the finger and apply the same force again to move the cursor up and down. So for selection, we asked the participants to apply 2 newtons of force on each sensors. So that the design of this type of pressure was really based on our previous work, so we can compare back to our lab studies. The second input technique we tested was a physical dial. So for this, we just used an off-the-shelf USB controller. So rotating clockwise, move the on-screen cursor down, anti-clockwise up. There's been lots of debates which way is which, but we just looked at the systems in the BMW and Mercedes systems and just followed those. And to select the target, we asked the participants just to press down on the dial. We had 2 touch conditions. One was simply directly selecting the target. So what you see here is that we want them to select the target highlighted in red. And the other touch condition was using on-screen buttons. So what you can see is the light blue highlights the current cursor position. And this is the same for the pressure-based buttons and using the dial. So we placed the dial and the 4 sensors on the 3D printed cases so that we can test haptic feedbacks with those conditions. So for that, we placed 1 surface transducers in each case. One thing I would say is that the dial doesn't have any mechanical clicking, so it allowed us to design our own haptic feedback. So we designed 2 tactile cues, One to a short vibration to inform the user each cursor movement, and a longer vibration to inform the selection of a target. So for our driving task, so a study took place on the public roads in Germany. We had legal and ethical requirements before running the study. We told all the participants that the main task was to drive in a safe manner and to perform the input task as best as you can. We had our experimenter sit at the front passenger side just to overview the studies, but he or she did not have control of the vehicle. The vehicle was manual. It was a manual gearbox vehicle, so it's more demanding than an automatic. And the participants drove a road that consisted of town and highway driving, so that we can vary the kind of typical driving situations. So for the study, we've got 26 participants, 9 females, 15 males. We managed to recruit a broad range of, a participant from a broad age range. For this study, we avoided recruiting drivers that were that held a license pretty new. So we used a within subject design. So there were 4 input techniques, 2 types of feedback, but we only had 6 conditions because we never evaluated the feedback conditions with the 2 touch conditions. So I'll just quickly go over some of the main findings. So in terms of target accuracy, so what you can see is that all the techniques performed really well. Haptic feedback, again, didn't really make much of a difference. I think one of the reasons was that the targets we used were quite large. So in terms of selection times, what you can see here is that directly select target was the quickest by quite a margin, which is not a surprise. Pressure-based buttons took the longest, almost 4 times longer than using direct touch, but haptic feedback had no effect on selection time. So we also recorded the user's visual attention, so we stuck a camera on the front windscreen. So what we found was that the pressure buttons result in highest number of glances towards the touchscreens, while touching the targets directly caused the longest duration per glance. But one thing we're quite happy to find was that haptic feedback managed to decrease the number of glances and the duration per glance for pressure-based buttons and the dial. So I'll just quickly summarize the study. So all input techniques performed well in terms of accuracy. Direct touch on the targets were the fastest method. Pressure-based buttons took almost 4 times slower. Pressure-based buttons also caused the most number of glances at the touchscreen, while directly selecting target resulting in the longest duration per glance. So just now it's very difficult to recommend a design of what we design for in-car list applications, but I think pressure could be useful for other applications, and variable tactile feedback can reduce visual attention for indirect controls. So thank you for your time, so I'm happy to take questions.
Hello, Nick Martellero, Stanford University. One thing I'm curious about is how much time did drivers have to sort of get used to the controls? Because I know that in my car, once I learn the touch buttons, I kind of know where they are, and I can sort of feel around. I don't actually have to look at them. And I noticed that the time for those was actually higher than I had expected.
Yeah, sure. So for this study, we basically gave them a really, I don't think it was a long enough training session. It was just really before we started the study, we obviously didn't, we just showed them how the technique worked, and once they were comfortable, we started the study. One thing I would say is that, I think through time, if they started learning how to use, so you would probably see a reduced in time for the controls.
Yeah, and then I guess in looking at that, looking at some of the results, the touchscreen seems to do pretty well on some of the things. What is your sense of actually maybe how people should incorporate touchscreens in cars, or what do you think about that?
Sorry, I didn't catch your last
Sorry, so given the results that you have, what are your thoughts now on sort of touchscreens versus these other haptic interfaces in vehicles?
I think, I think manufacturers like putting touchscreens, but it's quite cool and it's quite novel, so you can design new applications. But for this study, we didn't ask them, what one they preferred. But from our previous studies, a lot of people still like physical controls because you can grab onto them. And for touchscreens, one of the reasons why we didn't do the haptic feedback, because it's very difficult to provide enough haptic feedback on the touchscreen. So I think there's definitely a place for it, but I think there's also a place for like actual physical and like dials and buttons as well. So you see the Tesla example is a bit extreme without any actual physical buttons, but yeah.
Well, thank you.
Okay, thanks.